Hello, hello. This is vlog at G129. Currently, it is about 11 a.m. CST. I did not look at spin orbital pairing, but I got more into spin because I was trying to understand ways in which maybe my understanding of what spin is from the wave perspective, as opposed to it seeing as a particle and it having a quote unquote, but it has the wave has a magnetic moment. Of course, it does. But I was wondering, is like, sure, it may have a magnetic moment, but it doesn't mean that it exhibits it does exhibit characteristics of a something spinning in at least in the macro scale. But if you think about like a set of electrons in or you could just think of like a gyroscope, I guess, or like a spinning top, that has angular momentum. It's a set of particles moving in a circle, concentric circles, basically. And not only that, they actually have a direction that they're going in and whatnot. And I was thinking, I was like, okay, well, yeah, that is cool and all. And I was also thinking, I was like, okay, that's cool. There's another thing. There's also another thing that, okay, it's kind of hard to conceptualize at times, especially when you're thinking about like the mappings between like the particle and how similar they are to a wave. And I found something. There was an experiment apparently. This experiment is called was, I guess, called Larmor. Some kind of experiment done by Larmor back in, let me see, what year was that? Doesn't say it. But okay, there was an experiment done basically where they had a magnet. They had a huge magnet basically. So you had when you think of magnets, they have like lines, of course, and lines, force field lines. And when you think of electrons, they want to go inwards into it, of course, because the best way to think, well, I think of it is, how do I actually think of that? Why do I think of it? I haven't really thought of that either, but that's besides the point. It's a force field going up, and it's not gravity, but it's still a force field. And it basically, from what I can understand from Larmor precession, is that Larmor precession basically exhibits or shows that electrons have angular momentum due to the fact that there is a precession. It's a precession going around a what's that name called? I know there's the magnetic moment of that given particle is going around a point, which is actually that, not a point, I guess a line, but we can think of it as a point as well, a line, and that line is the actual force field, or the magnetic field and whatnot. And I was just kind of looking at it and all that. I was like, maybe, yeah, it does exhibit characteristics of a spinning top, and I don't really know how to explain it well, but also you can envision a spinning top to have concentric circles, and you can discretize it into shells to some degree because that still exhibits angular momentum, so you can kind of extract that away into a more shell-like structure. And I started thinking, I was like, well, I mean, also these peaks can exhibit, you can actually almost think of them as electrons with less charge, due to the fact that the difference away from the line, the zero line, is a little bit further. So it has, there is a relationship between energy and the amplitude of a given wave, so you can think of it like that. So what this means is that there can be electrons that are, potentially, you can almost think of it as concentric circles filled with quote unquote electrons with smaller charges, or less negatively charged particles, almost. Maybe you can think of it like that. And then you can think of that, and it kind of exhibits the characteristics of a spinning top, almost. You can think of it as shells. Now, you would have to ask us, like, why would it seem like that these charges are spinning? Like, That's another interesting thing. And I was thinking that maybe there could be a way to explain it, but it's very roundabout and it's not really rigorous to any extent. But pictorially, it does look like you can actually envision it as a spin. So I guess to some degree, electrons do spin, but not in the way that you think of it. Also, I was thinking, would that work actually? No, because again, looking in 2 dimensions, you can look at these other points as sources, just like the wave being the source here. There's another source here, going in all directions. But they seem to cancel each other out, but they still have a general momentum direction. There's still a direction in that way. It's kind of like it's a non-particle way of expressing it. It's still wave-like. And then you can think of that source as like another drop that goes along that intersects with that. So how I think of it is as it's like a bunch of waves, right? And then, but also these waves can also be seen as sources. And then these sources can then be seen as more concentric circles along. The main source is there, but then you can also think of other points as sources. That's the hard part to think about. And well, these sources will intersect with that concentric circle, and you can think of them. It will have a general trend going in one direction, but it will also have a general trend going in the other direction, which is interesting to think about. But now, I think there could be a way to connect that and explain it to it looking like it has angular momentum, but not in the way that we think of it. So, not in the way that we think of it. And I'd had to think about this more. Feynman has obviously talked about this, and the guy, I think he looked at this experiment, Larmor Precession, and he kind of came to the same conclusion. He says, yes, it exhibits angular momentum characteristics, but it doesn't necessarily mean that it's the conventional way that we think of angular momentum from a particle's perspective. We're thinking about it from a more of a wave-like perspective without all of the confusion behind what part, like, trying to, it seems like physicists are still trying to, they still have this conception of particles in their mind. I'm trying to break out of that and create a different, maybe framework of understanding waves and whatnot, and that seems to be a decent way with a decent way of explaining the angular momentum characteristics of a wave. Now, I haven't looked at all the math. Well, I mean, of course, I have all the math on here for, what is tau in this situation? Oh, torque of the magnetic moment. Oh, torque on the magnetic moment. It's called a torque because there's a force going this way and the magnetic moment is going this way, so it's kind of like trying to pull it in one direction, but since it's spinning, now I vaguely remember much about torque and all that, and gyroscopes are interesting because they stay fixed because it's the same characteristics, right? They stay fixed because of its I guess this angular momentum vector pointing this way and wants to stay there due to probably the conservation of angular momentum. There's probably some connection with that. I don't know. I don't remember. Yeah, but yeah, so that was cool, and I was trying to think of ways in which it's like, I mean, that line of logic cannot be defied, unfortunately. There's no way of like looking at that and saying that it doesn't exhibit angular momentum characteristics. It certainly does, at least from our perspective of it and our perspective of particles, but I think people just haven't taken the necessary steps to look at angular momentum from a wave point of view. I think that could possibly be the issue, but also difficult to think about, because I wouldn't even know how to approach a rigorous way of explaining what I just said with, I don't know, what's his name? There was a guy who was really interested in waves, and he thought about every single point of a field or wave can also be seen as a source. And it's true. Well, of the troughs. We're looking at the troughs, and we can think of each of those points as sources. As long as the main source has an external force keeping its energy the same, so it'll still transmit that data with a lower amplitude, because the lower amplitudes is because of tension. So I think what would be a way of explaining that? Yeah, something like that. I guess you can think of like its information at one point is kind of like dispersed all throughout the field, and via the conservation of energy or information, the field has no choice but to have lower troughs. If the amplitudes were the same, then obviously that would mean that the energy dispersed all throughout the field is larger than the source that was giving that information to the field. So you can't think of it like that, but yeah. So that I guess that's the reason why. That's how I think of it, at least. And I guess via tension, you can think of it like that too. Via impulse, because there's a reactive force that stops it from going to its main the amplitude of the actual source. I think of it as impulse. There are multiple ways of thinking it. I think the best way of thinking is from a conservation of energy point of view, and via proof of contradiction, you'd come to that conclusion. So I think that's a good way. So I think that's something to focus on for a little bit. Just because I'm interested in the concept of spin and quantum mechanics. For some reason, that caught my attention. I haven't looked at spin orbit duality. I still don't really know what that means yet, because I didn't look at that Wikipedia page. There were a lot of equations pertaining to it, so I don't feel like having to look into that now. Yeah. So far, that's what I've been thinking about, sort of. What else have I been thinking about? I guess I was also thinking about, like, just like the dual perspective of electromagnetic fields and whatnot, and again, being able to kind of think of the information imposed on the electromagnetic field is actually associated to the magnetic field by the change of it's just the change of the electric field induces a change in the magnetic field, and also the change of the so that means that the force that is imposed on it, inducing a change on there, is directly linked to the magnetic field. So I guess that's another way of thinking about why we get these dipoles along each. It's not just the source; it's coming from each of its peaks and troughs. So it's all of its peaks. I think that's probably the best way to think of it as, because then you can think of those peaks as again, point-like sources, and imagining it as a point-like source without the external force being imposed on it. It's just a thought experiment. But yeah, so yeah. And I think that can somehow be connected to what I said, precession of the wave. Precession of the wave. So, I mean, you would actually just think of a wave. You can think of it as a plane. So you'd be looking at the plane, and the plane would kind of be doing this almost, or at least the interaction of information with the plane is kind of moving like this. It's weird to think about, and I don't really feel like having to explain it. But you can also, how would it look like? It would be kind of like this, sort of, kind of like rotating on a. I don't know, it's kind of hard to explain. Of course, a plane wouldn't be moving, but you'd just be thinking of a wobbling plane. You know, with that you can also like think of a wobbling spinning top and just slice in half and then look at the top and then see how it kind of goes like that, almost like that. It's I don't know how to. I guess you could think of it as a disc. I guess you could think of it as a disc rolling on its edges like that or something. I don't know. I don't know. But yeah, I'm gonna look at that more. And I think that's a wonderful way of thinking of it. It's just it would be hard to express mathematically. And you'd also wonder, it's like, okay, that's cool and all, but wouldn't the other sources along that concentric circle of that peak, wouldn't they cancel out its movement in the other direction, in both directions? Because you have to imagine two sources. Actually, no. The interesting thing is, if you look at 2 points on that, let's say that we're looking at a circle, and there exists one point directly in between 2 other points. I know infinitesimals would be an issue here, because you would say, okay, there are infinitely many points between each and every other point, which is why real analysis is necessary to some of these frameworks and whatnot. But let's say that there's a point, and we're just going to ignore infinitesimals. Let's just ignore infinitesimals. Just keep it simple. And this point wants to go here. We can think of we're thinking of points going somewhere because these are wave functions, and they have a dx, right? And one would go here and the other one would go here. In the case in which you can think of, they don't really cancel out. They actually superimpose on each other to be bigger. So that's good. That's interesting. That's interesting. That is really interesting. Now, if you add a dt to it, I would like to see these minutiae, these very micro scale factors, because if you think of a dt involved, you can almost see the ripples between these is kind of going, these sources are going up and down, up and down, up and down, up and down. And then you look at the other one, as it goes up, the one next, the point next to it goes down. So you have these. Interesting. Very interesting. I wouldn't know how to explain that via motion and how that would even be considered to be motion to a degree. But I could exhibit that through its wave nature to some degree. You could also take the, Feynman's line integral. So you can actually take a line integral of one of these electrons, and then you can look at the possible paths it can take. So it goes from this point to the next, and it'll create a concentric circle. And actually, over time, there are line integrals that exhibit motion in the way that we think of particles. So that could probably be a solution to it. They're actually called path integrals. Sorry, there's a difference. I think there's a difference between line integrals and path integrals. Path integrals are integrals that are along some kind of parametrical system in like a line of some sorts, and these lines have values associated to them. You could think of it as like you could think of t and then like xy or something, like xy t, and then t at each point is going to be like some xy value. Then you can just take the line integral and add each quote unquote pointer, each dt to it, and then add it up to the total value. You see this in work. You have to take an integral over some kind of parametrical line or parametrical function, I guess you could say. That's the path is taking some function, And then you can look at all of its dt's because there's it's again f dx, but you're looking at the f dot dx. So then there's force at each every point, and then you think of delta x, but this delta x can be seen as like some n times dx. The n would be infinite in this situation, but let's not talk about that. Some n times dx, and yeah, you can create an integral out of that. Yeah, and that's how you can actually find the total work within any system with a force field that actually has a analytical function pertaining to that path it takes, of course. Yeah. So that's interesting, though. I think that's actually a good explanation of why waves tend to exhibit angular momentum characteristics. I didn't know you could think of it that way until I started thinking about it. I guess it's good. Yeah, I like to use my stream of consciousness because it actually tends to come up with interesting theories behind certain things. My brain likes to look at the why, so I force. What I usually do is actually force that's why I like looking at physics, because there are a lot of whys that people don't know how to explain yet. Maybe some people do, but they don't know how to explain it. That's the hardest part, is being able to explain it rigorously. And then for you to explain something like that rigorously, you'd have to somehow all I can say is that the path line integral is cancelled out when you take all possible paths of that electron from the point source point of view. Maybe I'm wrong. But also, you're thinking about these as different particles. Sorry, you're thinking about them as different particles. So these particles only exist on that circle. And then you can think of all the other ones, and that circle actually creates a line integral, like I said. And the only thing is that you can think of it from both ways. So would that cancel out? Why would it be spin? Yeah, so that's the only thing, is like why. It's interesting. I wouldn't be able to explain that, because it could go both ways, right? So you'd think it would cancel out or something like that. I don't know. Maybe that wouldn't work out. I wouldn't know. But yeah, it's still interesting to think about. Maybe somebody else can explain this for me. Anyways, I'm done talking. And I thought that was a nice little thought experiment. And maybe I will look into the spin orbit parity theory, or whatever it's called, just to be a little bit more acquainted with it.